Hello, cosmic explorers. Have you ever gazed at the night sky and wondered why we seem to be alone in this vast cosmic ocean? Imagine this. You're standing under a clear night sky, darkness enveloping you as countless stars twinkle above. Each of those distant points of light represents a sun, many with their own planetary systems. Yet amid this cosmic abundance, we hear nothing but silence. In the observable universe, we've identified over 2 trillion galaxies, each containing hundreds of billions of stars. Our own Milky Way alone harbors an estimated 100 to 400 billion stellar systems. The numbers are so vast, they become almost meaningless to our human minds. Think about this. There are more stars in the universe than grains of sand on all of Earth's beaches combined. Yet here we are, on our tiny blue planet, seemingly alone in this infinite cosmic dance. The silence is deafening, isn't it? This profound mystery brings us to today's fascinating journey into one of modern astronomy's greatest puzzles, the Fermi Paradox. I'm your host on Exploring the Universe. And today, we're diving deep into this captivating contradiction. We'll explore why, despite the overwhelming mathematical probability of alien civilizations existing, we haven't found a single trace of them. Not one radio signal, no megastructures, no space probes, nothing. This cosmic riddle has puzzled scientists, philosophers, and dreamers for decades. It challenges everything we think we know about life, evolution, and our place in the cosmos. Are we really alone? Are we looking in the wrong places? Or is there something more profound at play? The implications of this paradox are staggering. If we're truly alone in this vast cosmic ocean, what does that say about the rarity and preciousness of life? And if we're not alone, where is everybody? These questions cut to the heart of human existence and our cosmic significance. As we embark on this journey together, prepare to have your perspective challenged and your imagination stretched. We'll explore mind-bending possibilities, from ancient alien civilizations to the sobering prospect that we might be truly alone in the cosmos. Whether you're a seasoned astronomy enthusiast or just curious about our place in the universe, this exploration of the Fermi Paradox will forever change how you look at the night sky. Stay with us as we unravel this cosmic mystery. Remember to like this video, share it with fellow space enthusiasts, and subscribe to Exploring the Universe for more journeys into the unknown. Let's begin our quest to understand why, in a universe so vast and ancient, we still haven't heard a single hello from the stars. Let's travel back to a summer day in 1950, to a seemingly ordinary lunch break at Los Alamos National Laboratory in New Mexico. Picture this. A group of brilliant scientists, including Edward Teller, Herbert York, and Emil Konopinski, are having a casual conversation over sandwiches. Among them sits Enrico Fermi, the Nobel Prize-winning physicist who played a crucial role in developing the first nuclear reactor and was a key figure in the Manhattan Project. The conversation drifts to recent UFO sightings and a cartoon about alien spacecraft stealing trash cans from New York City streets. The scientists engage in light banter about the possibility of extraterrestrial visits and interstellar travel. Then, seemingly out of nowhere, Fermi interrupts with a disarmingly simple question that would reshape astronomical thinking. Where is everybody? This moment, known as Fermi's outburst, wasn't just a random query. Fermi, known for his exceptional ability to make quick mathematical estimates, later termed Fermi calculations, had been quietly contemplating the probability of extraterrestrial civilizations. He rapidly calculated that given the age of the universe, approximately 8 billion years, and the vast number of stars and planets, there had been more than enough time for advanced civilizations to colonize the entire galaxy multiple times over. The implications were profound. If intelligent life was common in the universe, evidence of its existence should be obvious. Alien civilizations should have visited Earth, established colonies, or at least left detectable signs of their presence. Yet we observe nothing but silence. In the years following Fermi's famous question, the paradox gained significant attention in scientific circles. While Fermi himself never published his thoughts on the matter, others began developing formal arguments around his observation. In 1975, Michael Hart published an influential paper that thoroughly examined the paradox, arguing that if extraterrestrial civilizations existed, they would have reached Earth long ago. The context of the 1950s adds another fascinating layer to this story. This was the height of the Cold War, when humanity had just developed the capability to destroy itself through nuclear weapons. The scientists at that lunch table were intimately familiar with humanity's destructive potential, which may have influenced their thinking about the survival prospects of technological civilizations. Since that fateful lunch in Los Alamos, the Fermi Paradox has spawned countless scientific papers, books, and theories. It has influenced fields ranging from astronomy and biology to philosophy and anthropology. The paradox has become more relevant than ever as we discover thousands of exoplanets and develop increasingly sophisticated methods to search for extraterrestrial intelligence. What makes this historical moment particularly poignant is that Fermi's simple question emerged from a casual conversation. Yet it encapsulated one of the most profound mysteries we face. In a universe so vast and ancient, our apparent solitude seems impossible. Yet here we are, still searching for our cosmic neighbors. The paradox continues to challenge our assumptions about life, intelligence, and our place in the universe, making Fermi's lunchtime question one of the most important scientific observations of the 20th century. To truly grasp the Fermi paradox, we must first comprehend the mind-boggling scale of our universe. Let me paint this cosmic picture for you in terms that might help visualize this incomprehensible vastness. Our home galaxy, the Milky Way, is just one among billions. Within its spiral arms alone, it harbors between 100 to 400 billion stars, but that's just the beginning. Current estimates suggest there are roughly 2 trillion galaxies in the observable universe. Let that sink in for a moment. 2 trillion galaxies, each containing hundreds of billions of stars. To put these numbers in perspective, imagine standing on a beach. Pick up a handful of sand and let it run through your fingers. Each grain represents a star, each with the potential to host its own planetary system. Now consider this, there are more stars in the observable universe than there are grains of sand on every beach in every country on Earth. In fact, multiply all the Earth's sand grains by 10,000, and you're getting closer to the number of stars out there. Recent discoveries have made this picture even more remarkable. Thanks to missions like NASA's Kepler Space Telescope and TESS, we now know that planets are not rare cosmic oddities, but rather the norm. Most stars host planetary systems. Our current data suggests that, on average, every star has at least one planet orbiting it. Many have multiple planets, just like our solar system. The numbers become even more staggering when we focus on potentially habitable worlds. Conservative estimates suggest there are at least 40 billion Earth-sized planets orbiting in the habitable zones of sun-like stars and red dwarfs in the Milky Way alone. The habitable zone, often called the Goldilocks zone, is the region around a star where temperatures could allow liquid water to exist on a planet's surface, a key ingredient for life as we know it. To further illustrate this vastness, consider that light, traveling at 186,282 miles per second, takes over 100,000 years just to cross our galaxy. The nearest major galaxy to us, Andromeda, is 2.5 million light-years away, and we can observe galaxies billions of light-years distant. In this cosmic ocean, our Earth is less than a speck of dust. We orbit an average star in an unremarkable part of a spiral arm in just one of trillions of galaxies. Our sun is just one small light in an endless cosmic arena. When we look up at the night sky, every tiny point of light we see represents a sun, many of which are far larger and more impressive than our own. Many of these stars are orbited by planets, some of which might harbor conditions similar to Earth. This incomprehensible vastness is precisely what makes the Fermi Paradox so perplexing. In a universe so enormous, with so many opportunities for life to emerge, the possibilities seem truly infinite. Even if life were an incredibly rare phenomenon, occurring on just 1 in a billion suitable planets, there should still be millions of civilizations out there. The sheer scale of the cosmos suggests that we shouldn't be alone. Yet, as we scan this cosmic ocean with our increasingly sophisticated instruments, we hear nothing but cosmic silence. This vastness, rather than resolving the paradox, only deepens it. With such an abundance of potential cosmic real estate, the question, "Where is everybody?" becomes even more puzzling and profound. In 1961, astronomer Frank Drake took a revolutionary step in quantifying our cosmic loneliness by developing what would become one of the most famous equations in astronomy. The Drake equation isn't just a mathematical formula. It's a framework for understanding the factors that could lead to intelligent life in our galaxy. The Drake equation, which estimates the number of detectable civilizations in our galaxy, is expressed as follows: n equals r star multiplied by fp, multiplied by ne, multiplied by fl, multiplied by fi, multiplied by fc, multiplied by l, where n, the number of detectable civilizations in our galaxy; r star, the average rate of star formation per year; fp, the fraction of stars that have planets; ne, the number of planets per star system capable of supporting life; fl, the fraction of suitable planets where life actually appears; fi, the fraction of life-bearing planets where intelligent life evolves; fc, the fraction of civilizations that develop detectable technology; l, the length of time such civilizations release detectable signals. When read aloud, the equation sounds like n equals r star times fp times ne times fl times fi times fc times l. What makes this equation fascinating is how it systematically breaks down the journey from raw cosmic materials to intelligent civilizations. It's like following a recipe from basic ingredients to a finished dish, where each step must be successfully completed to reach the final result. When Drake first presented this equation at the Green Bank Conference in 1961, many of these variables were complete mysteries. Today, thanks to modern astronomy, we can make much better estimates for some of the early factors. We now know that most stars have planets. Fp is quite high, perhaps 0.8 or higher, and we're getting better estimates of potentially habitable worlds. Ne might be around 0.4 for sun-like stars. However, the equation becomes more uncertain as we move toward its biological and sociological factors. We still don't know how readily life emerges given the right conditions, fel, or how likely it is for intelligence to develop, fi. The final variables about technological development, fc, and civilization longevity, l, remain highly speculative. Let's plug in some conservative modern estimates. R star equals 1 new star per year in our galaxy. Fp equals 0.8, meaning 80% of stars have planets. Ne equals 0.4, meaning 40% of stars have potentially habitable planets. Fl equals 0.1, meaning 10% of suitable planets develop life. Fi equals 0.1, meaning 10% of life-bearing planets evolve intelligent life. Fc equals 0.1, meaning 10% of intelligent species develop detectable technology. L equals 10,000 years, representing how long civilizations survive and remain detectable. Even with these cautious numbers, the equation suggests there should be several technological civilizations in our galaxy right now. More optimistic estimates can yield hundreds or thousands of civilizations. What's particularly intriguing about the Drake equation is how it evolves with our knowledge. When we discovered that most stars have planets, it dramatically increased our estimation of FP. The discovery of extremophiles on Earth, organisms thriving in seemingly impossible conditions, has made us more optimistic about FL, yet each answered question seems to spawn new ones. The equation has also sparked crucial discussions about civilization longevity. The L term might be the most critical factor. If technological civilizations tend to destroy themselves quickly, it would explain why we haven't detected anyone yet. This has led to serious discussions about existential risks and the importance of long-term human survival. While the Drake equation might not give us a definitive answer about alien civilizations, its real value lies in organizing our thinking about this complex question. It helps us identify what we know, what we don't know, and what we need to learn. It transforms a philosophical question into a scientific framework, allowing us to systematically approach the great mystery of our cosmic solitude. As we continue to refine our understanding of each variable, the Drake equation remains a powerful tool for contemplating our place in the cosmos and the likelihood of finding others out there in the vast cosmic ocean. Now we arrive at the heart of this cosmic puzzle. The Fermi Paradox represents one of the most profound contradictions in our quest to understand our place in the universe. After examining the vast numbers of stars and planets and understanding the Drake equation's implications, we face a perplexing reality: the cosmic silence. Consider this: our galaxy alone contains hundreds of billions of stars, many of which have existed for billions of years longer than our Sun. Even if interstellar travel is limited to a small fraction of light speed, an advanced civilization could colonize the entire Milky Way in a few million years, a mere blink in cosmic timescales. Yet we observe nothing. This silence manifests in multiple ways. We've detected no artificial radio signals, despite decades of searching. Our telescopes have found no signs of Dyson spheres or other megastructures that an advanced civilization might build. We've observed no evidence of interstellar spacecraft or probes, no artificial modifications of stellar systems, and no clear indicators of cosmic engineering at any scale. The contradiction becomes even more striking when we consider the timescales involved. Our galaxy is roughly 13.6 billion years old, while human civilization is barely 10,000 years old. This means that any alien civilization that emerged even a few million years before us would have had ample time to develop technologies far beyond our current capabilities. They could have established a visible presence in our cosmic neighborhood, yet we see nothing. Think of it this way: imagine walking into a vast forest that should be teeming with wildlife. You see perfect conditions for life: water, food, shelter, yet you hear no birds singing, spot no animals moving, find no tracks or traces. The silence itself becomes eerily significant. This is exactly our situation as we scan the cosmos. Perfect conditions for life abound, yet we detect no signs of other intelligent beings. The paradox deepens when we consider the various ways we might detect alien civilizations. Even if they weren't actively trying to communicate, an advanced civilization might be visible through their waste heat, their use of energy, or their modification of their environment. We should be able to detect what astronomers call technosignatures, the technological fingerprints of advanced civilizations. Yet our most sophisticated instruments reveal nothing but natural phenomena. This absence of evidence is particularly puzzling because we're not just looking for one type of signal. We're searching across the electromagnetic spectrum, from radio waves to infrared signatures. We're monitoring for unusual stellar patterns that might indicate artificial structures. We're even looking for anomalous chemical signatures in planetary atmospheres that could suggest industrial activity. The fact that we've found nothing across all these potential indicators makes the paradox even more compelling. Some scientists argue that we might be looking in the wrong places or in the wrong ways. Perhaps advanced civilizations use communication methods we haven't yet discovered. Maybe they're deliberately hiding their presence, or perhaps they exist in forms we can't recognize or understand. But these explanations themselves raise further questions. Why would every single civilization choose to remain hidden? Why would there be no exceptions, no rebels, no accidents revealing their presence? The implications of this paradox are profound. Are we truly alone in the galaxy? Are we the first technological civilization to emerge? Or is there something about the evolution of intelligent life that makes it incredibly rare? Perhaps most sobering is the possibility that technological civilizations tend to destroy themselves before they can establish a lasting presence in the cosmos. As we gaze into the cosmic ocean, our nets continue to come up empty. But each empty net tells us something important about the nature of life, intelligence, and technological civilization in the universe. The very silence that puzzles us might hold the key to understanding our unique place in the cosmos. Would you like to share your thoughts on this cosmic silence? What's your theory about why we haven't detected any signs of alien civilizations? Are we truly alone, or have we just not found our galactic neighbors yet? Your perspective is valuable as we explore this universal mystery together. Let's continue this conversation in the comments below. And don't forget to like this video if you're as intrigued by this cosmic paradox as I am. The Fermi Paradox extends far beyond theoretical contemplation, profoundly influencing multiple fields of science and human endeavor. Let's explore how this cosmic puzzle shapes our scientific pursuits and philosophical understanding. First and foremost, the paradox has revolutionized our approach to searching for extraterrestrial intelligence. SETI programs worldwide have evolved their methodologies based on the implications of Fermi's question. Rather than simply listening for radio signals, modern SETI efforts employ a diverse array of detection methods. Scientists now search for optical signals, analyze stellar light curves for artificial megastructures, and study exoplanet atmospheres for signs of industrial pollution or other technological signatures. The paradox has also catalyzed innovations in detection technology. For instance, the Breakthrough Listen initiative, the largest SETI program in history, processes massive amounts of data using advanced machine learning algorithms to identify potential artificial signals among the cosmic noise. These technological developments have applications beyond SETI, benefiting radio astronomy, data processing, and artificial intelligence research. In astrobiology, the Fermi Paradox has prompted scientists to reconsider what constitutes evidence of life. Researchers are developing increasingly sophisticated biosignature detection methods, from analyzing atmospheric compositions to studying chemical distributions that might indicate biological processes. This work has practical applications in understanding Earth's own biological systems and climate. The paradox significantly influences space exploration strategies. NASA and other space agencies now prioritize the search for biosignatures in our solar system, particularly on Mars, Europa, and Enceladus. The methods developed for these missions advance our general capabilities in planetary exploration, benefiting geology, chemistry, and environmental science. In planetary science, the paradox has sparked renewed interest in understanding habitable zones and the conditions necessary for life. This research has practical applications in climate science and our understanding of Earth's own habitability. Scientists are better able to model how planetary conditions evolve over time and how various factors interact to create environments suitable for life. The computational methods developed to address the Fermi paradox have broad applications. Models created to simulate galactic colonization patterns help us understand other types of expansion and diffusion processes, from the spread of ideas to population dynamics. These mathematical tools find applications in fields as diverse as epidemiology and social network analysis. In the realm of artificial intelligence and computing, the paradox has influenced the development of advanced signal processing techniques. The challenge of distinguishing artificial signals from natural phenomena has led to innovations in pattern recognition and data analysis that benefit many fields, from medical imaging to financial modeling. The paradox has practical implications for long-term human survival strategies. Understanding potential great filters, the obstacles that might prevent civilizations from becoming interstellar, helps us identify and potentially avoid existential risks to our own civilization. This includes improving our understanding of climate change, asteroid impact prevention, and the management of powerful technologies. In education and public outreach, the Fermi Paradox serves as an excellent tool for teaching scientific concepts. It introduces students to probability, astronomy, biology, and critical thinking in an engaging way. The paradox demonstrates how scientific reasoning can approach seemingly impossible questions. The philosophical implications have practical effects on how we approach long-term planning and space policy. Questions about our cosmic significance influence decisions about space exploration funding, international cooperation in space, and the development of protocols for potential extraterrestrial contact. In technology development, the paradox influences how we think about interstellar communication and travel. This has led to practical research in propulsion systems, communication technologies, and long-term space habitat design. Even if we never contact alien civilizations, these technological developments benefit human space exploration. Finally, the paradox affects how we approach conservation and environmental protection on Earth. Understanding the possible rarity of life in the universe reinforces the importance of preserving our biosphere and managing our technological development sustainably. The Fermi Paradox thus serves as a unique bridge between theoretical science and practical applications, driving innovation across multiple fields while reminding us of our unique responsibility as the only known technological civilization. Its implications continue to shape how we approach some of humanity's greatest challenges and opportunities. The paradox remains not just a scientific curiosity, but a catalyst for practical advances in technology, methodology, and our understanding of life itself. As we continue to search the cosmos, each new development inspired by Fermi's question brings us closer to understanding our place in the universe, while advancing our capabilities here on Earth. To deepen our understanding of the Fermi Paradox, let's explore the perspectives of leading scientists in the field of extraterrestrial intelligence research. Their insights offer crucial context and nuanced interpretations of this cosmic puzzle. Dr. Jill Tarter, one of SETI's most prominent scientists and the inspiration for the protagonist in Carl Sagan's Contact, provides a compelling perspective. She argues that the Fermi Paradox isn't truly a paradox at all, but rather an argument from incomplete evidence. In her words, our search for extraterrestrial intelligence so far has been equivalent to scooping one glass of water from Earth's oceans to determine whether fish exist. The fact that we found no fish in that glass doesn't mean the oceans are empty. This perspective is echoed by Dr. Seth Shostak, senior astronomer at the SETI Institute, who emphasizes the temporal aspect of our search. He points out that we've only been capable of detecting potential alien signals for about 60 years, a mere blink in cosmic timescales. Our search has covered only a tiny fraction of the potential communication frequencies and has focused on a relatively small number of star systems. Astronomer Jason Wright from Penn State University offers another important perspective. He suggests that we might be looking for the wrong signs. Traditional SETI focuses primarily on radio signals, but advanced civilizations might use communication methods we haven't yet discovered or imagined. He advocates for techno-signature searches, looking for physical signs of technological activity rather than just communication signals. Dr. Sara Seeger, an MIT astrophysicist, brings a different angle to the discussion. She focuses on the search for biosignatures rather than direct signs of intelligence. Her work suggests that we might first detect simple life forms through atmospheric analysis of exoplanets before finding intelligent life. This could help us understand the prevalence of life in general and inform our search for intelligent civilizations. Professor Abraham Loeb of Harvard University presents a more provocative perspective. He argues that we might have already encountered evidence of extraterrestrial intelligence, but failed to recognize it. His analysis of the interstellar object Oumuamua sparked intense debate in the scientific community about how we identify and classify potential evidence of artificial origin. Dr. Frank Drake, creator of the Drake equation, maintained until his passing that the key to the paradox might lie in the longevity of technological civilizations. He suggested that advanced civilizations might typically destroy themselves or alter their form so dramatically that we couldn't recognize them, explaining their apparent absence. Astrobiologist Dr. David Grinspoon offers an intriguing perspective on the temporal aspect of civilization development. He suggests that we might be in a transitional period where civilizations are gradually emerging across the galaxy, and we happen to be among the first. This early arrival hypothesis would explain the current silence, while suggesting that the galaxy might become more populated with technological civilizations over time. Dr. Michio Kaku, theoretical physicist and futurist, approaches the paradox from a technological perspective. He suggests that truly advanced civilizations might exist in forms we can't comprehend, perhaps having transformed themselves into post-biological entities or existing in dimensions we can't yet detect. These expert opinions share a common thread. They emphasize the vastness of both space and time and the limitations of our current search methods. They remind us that absence of evidence isn't evidence of absence, particularly when we've only scratched the surface of possible search strategies. The experts also highlight the importance of expanding our search parameters. As Dr. Tata often emphasizes, we need to look in more places, in more ways. This might include searching for different wavelengths of electromagnetic radiation, looking for artificial structures around stars, or developing entirely new detection methods. Most significantly, these scientists agree that the Fermi Paradox serves as a valuable framework for scientific inquiry, pushing us to improve our search methods and expand our understanding of what constitutes evidence of life and intelligence in the cosmos. Their perspectives remind us that we're still in the early stages of our search for cosmic companions, and the greatest discoveries may lie ahead. The collective wisdom of these experts suggests that rather than being discouraged by the current silence, we should be inspired to search more thoroughly and creatively. Their insights drive home the point that our search for extraterrestrial intelligence is not just about finding aliens. It's about understanding our place in the universe and the nature of life and intelligence itself. Let's explore some mind-bending facts about the Fermi Paradox and our cosmic search for alien life. Did you know that light's finite speed creates a cosmic time delay in our observations? If an alien civilization 65 light-years away were observing Earth right now, they would be seeing our planet as it was during World War II. This means that potential alien observers would be witnessing our history unfold in real time, seeing events that we consider long past. Consider this remarkable fact. The radio signals from our first TV broadcasts are now about 80 light-years away from Earth, creating what astronomers call our radio bubble. These signals carry episodes of I Love Lucy, early news broadcasts, and the first television commercials into space, potentially providing distant civilizations with their first glimpse of human culture. Here's another fascinating perspective. Our galaxy is so vast that if an alien civilization sent us a message from near the galactic center, it would take roughly 25,000 years to reach us. This means if they sent a message when humans were painting cave art, we would only be receiving it now. Speaking of scale, if we could compress the age of the universe into a single Earth year, modern humans would only appear in the last 14 seconds of December 31st. Our entire recorded history would occupy just the final second of that cosmic year. This really puts into perspective how young our civilization is compared to the age of the universe. Surprisingly, scientists have calculated that an advanced civilization traveling at just 10% of light speed could colonize the entire Milky Way galaxy in about 10 million years. While this might sound like a long time, it's less than 0.1% of our galaxy's age. This makes our cosmic silence even more puzzling. One particularly intriguing fact is that we've already identified over 5,000 exoplanets, and some estimates suggest there could be up to 40 billion potentially habitable Earth-sized planets in our galaxy alone. Even more amazingly, some of these planets are far older than Earth. The planet Kepler 452b, sometimes called Earth's cousin, orbits a star 1.5 billion years older than our Sun, giving any potential life there a significant head start. Consider this thought-provoking fact. Quantum entanglement could theoretically allow for instantaneous communication across any distance in the universe. Some scientists speculate that advanced civilizations might have mastered this technology, making our search for radio signals obsolete. We might be like ancient Romans, looking for smoke signals while missing phone calls. Here's something to keep you up at night. The dark forest theory, inspired by science fiction author Lewis Hickson, suggests that the universe might be silent because all intelligent life learns to hide. The theory proposes that civilizations stay quiet out of fear, knowing that revealing their location could attract attention from potentially hostile advanced species. Perhaps one of the most humbling facts is that our most powerful radio telescopes could probably not detect Earth's own radio signals if they were coming from even the nearest star system, Alpha Centauri. This raises the possibility that numerous civilizations might exist, but simply lack the ability to make themselves known across interstellar distances. Finally, here's a mind-bending possibility. Some scientists suggest that advanced civilizations might have evolved beyond biological form into a digital existence. If true, they might inhabit the quantum realm or exist in ways completely unrecognizable to us. We might be looking for biological signatures while advanced aliens live as information patterns in the fabric of space-time itself. These fascinating facts remind us that the Fermi Paradox isn't just about distant aliens. It's a mirror that reflects our own place in the cosmic story, our technological limitations, and the boundless possibilities that await us as we continue our search for cosmic companions. The universe is not only stranger than we imagine, it may be stranger than we can imagine. The search for extraterrestrial intelligence faces numerous challenges, but emerging technologies and innovative approaches offer promising solutions for the future. Let's explore both the obstacles we face and the exciting developments on the horizon. Our current primary challenge lies in the sheer scale of the search. The observable universe contains over 2 trillion galaxies, and even our home galaxy, the Milky Way, has hundreds of billions of stars. Our most advanced detection methods can only examine a tiny fraction of these potential habitats for life. It's like trying to find a specific grain of sand on all the beaches of Earth while only being able to look at a handful of sand at a time. Technical limitations present another significant hurdle. Current radio telescopes, despite their impressive capabilities, could barely detect a civilization like ours from even the nearest star system. The signals we send into space become increasingly weak with distance, making detection of artificial signals from distant civilizations extraordinarily challenging. Additionally, our search has primarily focused on radio waves, which might not be the preferred communication method of advanced civilizations. However, the future holds tremendous promise. The James Webb Space Telescope, launched in late 2021, represents a quantum leap in our ability to study exoplanet atmospheres. This revolutionary observatory can detect potential biosignatures like methane, oxygen, and other chemicals that might indicate the presence of life. Future missions will build upon this capability, potentially allowing us to identify signs of industrial pollution or other technological signatures in distant atmospheres. Ground-based astronomy is also entering an exciting new era. The extremely large telescope, currently under construction in Chile, will feature a primary mirror 39 meters in diameter. This behemoth will collect more light than all existing professional telescopes combined, enabling us to study exoplanets in unprecedented detail and potentially detect signs of alien civilizations that are currently invisible to us. Artificial intelligence and machine learning are revolutionizing how we process astronomical data. These technologies can analyze vast amounts of information, identifying patterns and signals that human observers might miss. Advanced AI algorithms are already helping SETI researchers distinguish potentially artificial signals from natural phenomena, and their capabilities continue to improve exponentially. Quantum computing represents another game-changing technology on the horizon. These powerful computers could process astronomical data sets that are currently too complex for classical computers to handle efficiently. They might also help us better understand quantum communication methods that advanced civilizations might be using. Interstellar exploration is advancing as well. Breakthrough Starshot, an ambitious project to send tiny spacecraft to Alpha Centauri, could provide our first close-up look at another star system within our lifetime. Similar initiatives could eventually allow us to explore promising exoplanets directly, rather than relying solely on remote observations. The development of new search strategies is equally important. Scientists are expanding beyond traditional SETI methods to look for technosignatures like Dyson spheres, industrial pollution, or artificial light signatures. Some researchers are even developing methods to detect quantum communications or gravitational wave signatures that might indicate advanced technological activity. International collaboration is increasing, with more countries joining the search for extraterrestrial intelligence. This global effort brings diverse perspectives, new resources, and innovative approaches to the challenge. The creation of international research networks allows for continuous monitoring of the sky and sharing of data and discoveries. Perhaps most excitingly, we're developing the capability to detect life directly through biosignature gases in exoplanet atmospheres. Next-generation telescopes will be able to analyze the chemical composition of atmospheres around potentially habitable worlds, possibly providing the first evidence of life beyond Earth. Public and private investment in space exploration continues to grow, driving technological innovation and expanding our search capabilities. Commercial space companies are developing new technologies that could accelerate our ability to detect and potentially communicate with alien civilizations. As we look to the future, the integration of multiple search methods, advanced technologies, and international collaboration offers our best hope of solving the Fermi Paradox. While the challenge remains immense, our tools and methods for searching the cosmos are becoming more sophisticated with each passing year. The question isn't just whether we'll find evidence of extraterrestrial intelligence, but when and how such a discovery might transform our understanding of our place in the universe. As we conclude our exploration of the Fermi Paradox, let's reflect on the profound implications of this cosmic riddle that has captivated minds for over 7 decades. Our journey through the vastness of space and time has revealed a universe that seems perfectly suited for life, yet mysteriously empty of detectable intelligent civilizations. Throughout this exploration, we've encountered mind-bending numbers that highlight the paradox's significance. We've learned about billions of galaxies, each containing hundreds of billions of stars and countless potentially habitable planets. The sheer scale of cosmic real estate available for life to emerge and evolve is staggering. The age of our universe, approximately 13.8 billion years, provides ample time for countless civilizations to have developed, thrived, and perhaps even colonized vast regions of space. We've examined various potential explanations for the great silence we observe. From the sobering possibility of the Great Filter, suggesting that some insurmountable obstacle prevents civilizations from reaching interstellar capabilities, to the intriguing zoo hypothesis, proposing that advanced civilizations might be deliberately avoiding contact with emerging species like ourselves. Each explanation carries its own implications about the nature of life, intelligence, and technological development in the cosmos. The Drake equation has provided us with a framework for understanding the factors that influence the emergence of detectable civilizations. While some variables in this equation are becoming clearer through modern astronomical discoveries, others remain profound mysteries that touch on fundamental questions about the nature of life and intelligence itself. Our search methods continue to evolve and improve. From traditional radio astronomy to the hunt for technosignatures and biosignatures, we're casting an ever wider net into the cosmic ocean. The development of more sophisticated telescopes, detection methods, and analysis techniques promises to expand our search capabilities dramatically in the coming years. Perhaps most importantly, the Fermi Paradox serves as a humbling reminder of our current place in the cosmic story. Whether we are truly alone, temporarily alone, or simply haven't yet detected our cosmic neighbors, the implications are profound. If we are alone, it suggests an extraordinary responsibility as the universe's known torchbearers of consciousness. If we're not alone, our eventual contact with other civilizations could fundamentally transform our understanding of existence itself. The paradox challenges us to think on cosmic scales while remaining grounded in rigorous scientific methodology. It reminds us that the most fundamental questions about our existence — are we alone? Are we typical? What is our cosmic significance? — remain unanswered, but perhaps not unanswerable. As we continue our search for answers, the Fermi Paradox stands as both a challenge and an inspiration. It drives technological innovation, sparks philosophical debate, and fuels our cosmic imagination. The very act of grappling with this paradox has advanced our understanding of astronomy, biology, and our place in the universe. Whether the solution to the Fermi Paradox reveals a cosmos teeming with life or confirms our cosmic solitude, the quest for understanding enriches our perspective and expands our horizons. It reminds us that we are part of something vastly larger than ourselves, participants in a cosmic drama that has been unfolding for billions of years. The silence of the cosmos may be deafening, but our determination to understand it speaks volumes about human curiosity and resilience. As we continue to search the stars for signs of other intelligence, we're not just looking for aliens, we're looking for context about our own existence, our own potential, and our own cosmic destiny. The Fermi Paradox remains not just a scientific puzzle to be solved, but a mirror reflecting our deepest questions about who we are and what our place might be in this vast, mysterious universe.